Okay, where are we at? Okay, so you guys did up to and including, did you do page 73? Did you do page 74? Okay, so we don't remember that. Okay, so we'll just hang out for a moment here. No, that's okay. Okay, that's all right. We are on page 84. Thank you for asking. It's 83. Oh, it's 83. Okay. So, an ionic bond. Are we familiar with the concept of an ionic bond? Yes. It is the attraction of a cation for an anion. So it is that attractive force between a cation and an anion, that is what an ionic bond is. And it results from the transfer of electrons, which we are going to be learning how to draw today, the transfer of electrons from one atom to another atom. It says, remember, smaller nonmetals are more electronegative. You guys probably don't know what electronegative is yet, so don't worry about that too much. Okay, we'll just hang out with that. When you are naming an ionic compound, the metal is always named first. Okay, so the metal comes first. The nonmetal comes second. And the nonmetal ends in "ide." So sodium fluorine becomes sodium fluoride. And don't forget, a formula unit is a single unit of an ionic compound, yes? So for example, Ca3N2 that would be a formula unit of calcium nitride, okay? 2 plus, 2 plus, 2 plus, 3 minus, 3 minus, and there we go. So what we're going to do is we are going to use Lewis structures and arrows, so both Lewis structures and arrows. So if you're showing this process, if you don't show the arrows, are you showing it all? No. Because the arrows illustrate the transfer of the electrons from the metal to the nonmetal. And once we have done that, we write the Lewis structure of the compound. We're going to write the formula unit of the compound. And then, because we can, we are going to name the compound. So let us start with sodium and chlorine. And I'm actually going to do it just up above. Okay, so we can kind of do it from scratch. So you might want to actually cover up the answer part. You know, if you've got an extra piece of paper or your periodic table, throw it over top. So if you have sodium, what is the Lewis structure for sodium? Sodium has One valence electron, absolutely, okay? And we are putting that together with chlorine. How many valence electrons does chlorine have? 7, it's in group 17. And in fact, if I wanted to be really clever, I could even do this in a different color. So I could see the difference in the 2 electrons. Or if you don't have different colors, one thing you can do to make it look a little bit different is instead of using a dot, this one you could use an X, okay? And then it looks different without having to have various colored pens. Yes? So in order to empty out the sodium and fill the chloride, we are going to show an arrow moving that electron from the sodium to the chlorine. Okay, so be sure to show the arrow. And what we will end up with is we will end up with Na. Na just lost an electron. What is its charge? Plus. And chlorine, here we go, we're going to draw chlorine. We got this one, this one, this one, this one, this one, this one, this one. And now we have that extra one from the sodium. And because we want the charge to be on that entire compound, what did we do with a Bohr model when we wanted to show the charge on an ion? We put brackets and the charge. We're going to do the same thing with a Lewis structure. We'll put brackets and the charge. We don't always put it on the cation because the cation doesn't really have any dots around it, so it's not like it's this whole huge structure that needs it, but you could put it around the sodium as well if you wanted to, okay? So now that we have that compound, we're going to write the formula unit of the compound, which is just the formula of the compound. And we know that it's NaCl, but the reason that we know it's NaCl is because we have one Na here, and we have one Cl minus, and therefore we have NaCl. And the name, of course, we would name it, we would say, oh, we have sodium chloride. Okie dokie. So you can see what I've shown here is pretty much what I've done. I didn't put the brackets. Like I said, the brackets, you know, you can use them if you want to. You don't have to. Yes. I'm going to come closer because it's a little noisy. Oh, the 3 dots. Yeah, that's therefore. 3 dots means therefore. Very useful because therefore is a long word. But if you can just use the 3 dots, it's much nicer. Now we're going to do the same thing with magnesium and oxygen, and I'm going to do magnesium and oxygen over here. So we have Mg. What group is Mg in? 2. So how many valence electrons? 2. I'm going to make them X's. Oxygen. Oh. What group is oxygen in? It's in group 16, therefore it has 6 valence electrons, Ve for valence electrons. So we're going to put those on 1, 2, 3, 4, 5, 6. What's the next thing we show? We show the movement of the electrons. How do we show the movement? We use arrows. So where does this X go? down into the little gap there. And the other one goes into the other little gap on the bottom, yeah. Okay, so now we redraw it. We say, okay, that's what we got. Very nice. So we now have MG. Does it have any dots or X's around it? Nope. And we have O. And it has 1, 2, 3, 4, 5, 6 red dots and 2 X's. It's your choice whether you put the brackets on there or not, okay? What will we write beside the MG? We're going to write 2 plus because it lost 2 electrons. And the O, what are we going to write beside the O? Yes, sorry. Does it matter where the X's go? No, it doesn't. I tend to put the little holes close to the other elements so that drawing my arrows is more convenient, but it really doesn't matter. Yeah? What are we going to write beside the oxygen? It gained 2 electrons. So what do we write? 2 minus. Okay? So far, so easy? Yes. Now, what if we have something a little more complicated? Sodium, oh, I forgot we were going to write the formula, which is just going to be MgO, because there's one Mg, one O. And we're going to write the name. What is the name of this compound? Magnesium oxide. Okay. Now we're going to work with sodium and oxide. We're going to use arrows to show the movement, and we go, oh, yay, that little sodium's X can fill in that gap right there. What problem do we run into? Oh yeah, there's like another hole right here. What's happening with this little hole? Ah, whatever shall we do? You're gonna add another Na so that we have enough, okay? So here we go. We'll put that one in there. Now we have Na, which is positive. We have Na, which is positive. And we have a single O that has its 1, 2, 3, 4, 5, 6 red electrons and 2 black electrons. And the charge of that oxygen is 2 negative because it gained 2 electrons. So our formula, what is our formula? Na subscript 2 because we have 2 NAs and we have 1 O, and so our formula then is Na2O, and the name is sodium oxide. So we do one last nasty one. Okay, this is as bad as it's going to get. It is, we're gonna skip MgBr2, we're gonna go with magnesium and nitride. Magnesium, 2 valence electrons. Nitrogen is group 15. How many valence electrons? 5. 1, 2, 3, 4, 5. So we have 1, 2, 3 little gaps, yes? So we'll take 1 electron and move it in here. We'll take a second electron and move it in here. Oh no! What's wrong? The drama is killing me. What's wrong? There's not enough electrons for the, oh my God! The nitrogen is still sad. Oh. What shall we do? Let's bring in another magnesium. We'll make it okay. Mg. Here we go. Ah, excellent. Let's move that electron and fill that gap. And we will make nitrogen all happy. Yes? But wait. Have we fixed everybody? No, what's wrong? Mg, oh, is sad. So what could we do? Add another n, we could be here forever, but we won't be. 1, 2, 3, 4, 5. And so this one plops into here. Hooray. We must be done at this point because magnesium is now happy. But we're not done. Why not? The tragedy. Who could come to our rescue? Another Mg. What's that? I'm recording. So if you ever want to watch this enthralling drama play again, you can do so. Okay, and here we go. Here we go. Yeah, and so now we have this. Now, you have two options as to how you write this out. You can write it like Mg2 plus, Mg2 plus, Mg2 plus, and then you can draw your N and your N, and then fill in those electrons, la 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 la, la 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 la. And then you can go, okay, 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 okay. 3 minus, 3 minus. By the way, what do you notice about the overall positive charge? 6. What do you notice about the overall negative charge? -6. Compounds are all, I know, compounds are always neutral. Are always neutral. Always. Not sometimes, always. Not even like one of these little things where I'm like, oh, I'm lying to you. Next year we'll teach you something different. No, always. How do we write the formula for this? It would be Mg what? 3, and then N 2, and what do we call it? Magnesium nitride. Okay, excellent. All right. Now, let's say you didn't want to write out all of this. You could also say 3 Mg2 plus, and you could write 2 N three minus. That would also be okay if you chose to do it that way. All right, it depends which one you think is more work. I'm not really sure. Quite frankly, that's a bit of work no matter what you do with it, okay? But you're never gonna get more than one question that's like that. I'm not gonna make you do something like manganese 7 oxide. Nope, we will not make you do that. What would the, if I have manganese 7, not that you could do this anyway because manganese is a transition metal. And do we know how to draw Lewis structures for transition metals? Nope, they don't work. But let's just say we had manganese 7 oxide. What does that 7 tell you? You remember that? It means the charge of manganese is 7 plus. This is a little preview of next unit, okay? And what's the charge of oxide? You should be able to tell oxide from looking at your periodic table. -2. How did you know it was -2? Because it's there, right? It's in that group. Yeah. But it is in group 16, so it has 6 valence electrons, so it wants to gain 2 electrons, so its charge is -2. How could you make this compound neutral? Yes. Yeah, double the manganese and have 7 oxygens. You're essentially finding the lowest common multiple of each, which is 14. So if you take this and you multiply it by 2, you're going to get 14 positives. And if you take this and you multiply by 7, you're going to get 14 negatives. But of course, we don't write compounds like that, right? We write them like this, Mn, and if we want 2 of them, we write the 2 down here. And then we have the oxygen. We don't write times 7, we write the 7 down there. And we don't write the charges when they're in there. Like I said, this is next unit, but it is review from previous years. So I thought I would just do a little introduction there. Okay. How about you guys do some of these exercises for about 10 minutes or so? Yes? So page 84 to 85. Just work on those for a few minutes. You don't use equal sign, just use an arrow. Yeah. Folks, scandium has 3 valence electrons, just in case you're wondering if you're like, oh my gosh, I don't know about scandium. Scandium has 3. I have a pencil here somewhere.
So instead of having them here, we should probably.
Yeah, instead of having them here and then two of them here, you would have, and there's no charge on this yet, right? Because it's neutral.
Yeah.
So we would have one here, and one
Yeah,
here.
Pair up when like
yeah.
the charges.
And then you're going to show the motion of these electrons. This one's going to move here.
Oh, okay.
This one's going to move into the second one. That's going to move to the third one. So now you're absolutely correct. We have scandium 3+, because it's lost 3. And we have 3 of those, so that's correct. And then you'll write the name scandium fluoride. Okay, so just be careful with that. Maybe go through and correct the ones where you've got them paired up. Like this one should be 1 here and 1 here. Yeah, same thing for sulfur. It should be like 2, 2, 1, 1.
Got it.
Okay. How are you doing? Good? All right. I would like to cover one more thing today because I won't see you for class tomorrow, and that means that, over the weekend I'd like you to be working on a few things. And what we're going to do is we are going to take a look on page 87. Page 87. So, we're actually going to learn how to draw. We're going to learn later. We're going to learn later how to draw. We're going to learn later how to draw more complicated covalent compounds, but these are only the most simple covalent compounds. But we are still trying to achieve that full outer shell. Now, these are covalent compounds. What do they do with their electrons? They share electrons. So there's going to be no arrows. Nobody's giving the electrons to the other guy. That's not happening, okay? So they're just sharing, okay? So let's illustrate this with the simplest one possible. Here we have hydrogen. Now we have to remember hydrogen, if I was to draw a Bohr model of hydrogen, I would have a proton in the center because it's atomic number 1, and I would have one electron around the outside because protons and electrons in an atom have to be equal. How many electrons fills up shell number 1? 2 electrons fill up shell number 1. So even though I will usually say we need 8 electrons to fill a shell, you have to remember that for hydrogen, hydrogen only needs 2. Everybody else is going to need 8. Okay, but hydrogen only needs 2. So each hydrogen atom starts with a single electron. Is that stable? No, but what if we said, let us share these 2 electrons, let's come together. And so now my electron is your electron and your electron is my electron, and the more we get together, the happier we'll be. Do you guys know that song? No? The more we get together, okay, yes. Sorry, I had a child at one point and we sang that. Yeah, anyway. We can use circles to show that those 2 electrons belong to each hydrogen. Yes? We can say, oh, look, this hydrogen here has those 2 electrons. And this hydrogen on the right also has those 2 electrons. I really just wanted to make that green color in the middle because I thought that was fun. Okay, so there's 2 electrons on the hydrogen on the left. There's 2 electrons on the hydrogen on the right. That fills up that first shell and everybody is happy. Now, you can leave your Lewis structure like this. This is correct, but often with covalent bonds, we will replace in covalent bonds only we will replace the 2 dots with a line representing the covalent bond. electrons are in that line? A line is equal to 2 electrons. Okie dokie. When you share one pair of electrons, 2 electrons is equal to 1 pair of electrons. If you share one pair of electrons, that is called a single bond. The single bond, double bond only applies to covalent compounds, okay, or covalent substances. This is a covalent element. Now let's consider fluorine. Fluorine is in group 17, so it has 7 valence electrons, and I have left the little gaps so that they're kind of beside each other, yes? Right, so I can look and be like, oh, look, they each have one that they could share with the other. So those guys are going to get together and share. And if we draw that, what would it look like? We would have 2 electrons in the middle. We would have 2 electrons on each side. And if you don't like drawing all the dots, if you prefer to draw X's, you can use X's. It doesn't matter. How could we change this so it's a little easier to look at? We could replace these 2 dots with a line, but leave all the other dots. Yes. You can leave it like this. I would recommend not doing it because the moment we get into more complicated structures, it is ugly, okay? Like it's just, it becomes like, you know, cringe inducing, okay? Now, this pair of electrons forms a bond. Therefore, we call that pair a bonding pair, okay? This right here is a bonding pair of electrons, okay? Same thing if we, you know, just have drawn them as 2 dots in between, that's a bonding pair. And that's one of the reasons why it's kind of nice to replace it with a line, is that it clearly shows the bonding pairs as lines. Pairs on the outside, non-bonding pairs, are called lone pairs because they are alone, they are not being shared with anyone else. Lone pairs is what we call non-bonding pairs of electrons. So you could count these up and you could be like, oh, look, I have, how many lone pairs are on this structure? 1, 2, 3, 4, 5, 6. And how many bonding pairs? 1. Okay. All right, so this is kind of just showing what we did here. You can see that we have 8 electrons belonging to the atom on the left, and we have 8 electrons belonging to the atom on the right. Is 8 a good number? 8 is a perfect number because we are shell number 2. In fact, any of the shells after that, we're going to go with 8. Even though there's other stuff happening, even if we get down into row, you know, 3 or row 4, row 5, okay, because the Lewis model just does those 8, all right? Here we have them labeled, we have our bonding pair, we have our lone pairs, and then we have, guess what? A practice exercise. Could you draw a Lewis dot electron dot diagram to illustrate the covalent bond formation in Cl2? You are going to show the original atoms. I'm talking to you in the back row there, Ben. You're going to show the original atoms. You're going to draw the molecules both ways. You're going to show them all dots, and then you're going to replace the bonding pair with a dash. We're only doing this one, so it's not like it's going to take up quantities of your time. Now, technically, you don't have to show the 2 chlorines with different styles of electrons, but it does kind of make it nice so you can see which ones came from where. Yes? You know when to covalently bond. So covalent bonds, that's going to be a nonmetal and a nonmetal. Yep. And so if you're doing the ionic bonding, that's going to be a metal and a nonmetal. You know what? You guys have 2 quizzes next week, so I was actually thinking of sending you home over the weekend to really study well for those. Yeah? Yeah. And if you already know how to do it all, then you have a lovely weekend ahead of you. Row is across. Okay, so think about it as like, yeah, you row a boat and it goes this way. It does not go this way. Yes. And think of this. If you go to a building in Greece, which way do the columns go? Up and down, right? Like, so if you look at the Parthenon or whatever, the columns go up and down. But the canoe one is good, okay? But one does not row a canoe, one paddles a canoe, but that's okay. I'll let that go. A rowboat, a rowboat. A dinghy, a dory. Okay. So your homework Finish enough of 3.2 to feel ready for your quiz. That's on Monday. 3.2 is atoms, ions, isotopes. It's all on the team where you go and you click on like upcoming quizzes. Okay. That's the isotope form. Now, I know you're all desperate to get out of your seat, but we do have 5 more minutes and you have another quiz. No, just a second one. This is number 1. But if you try and memorize everything for the quiz number 2 all on Tuesday night, that's not going to go well for you. So how does one go about memorizing things? You start now, you do a little bit of review today, you do a little bit of review tomorrow. You don't spend like 2 hours on Tuesday desperately trying to memorize it, although I imagine it would be more like 15 minutes if I'm being realistic. So instead of doing that, spend 15 minutes, each day of the weekend, Friday, Saturday, Sunday, you have a nice long weekend, looking at study for quiz number 2 on Wednesday, and that is on the periodic table, metals and nonmetals. Hi. I know it's really bright. Yeah.
Is it okay if I do it sooner? Because I don't want to be like.
Yeah. It's totally fine. Yeah.
Do you think I could maybe come in tomorrow?
Yeah.
And, like flex?
Do you want to come in during flex, and then if you need to like finish up after school or whatever, you can? Is there a particular section that you did better on than another?
Yeah, I think I just messed up the Ionic version just